So I am Leslie Harwood. I'm a research associate at Virginia Tech Transportation Institute and in the Center for Advanced Automotive Research. Also the program manager for the Safety Through Disruption National University Transportation Center, which is led by Virginia Tech. And today I'm going to talk with you a little bit about creating models of the environment surrounding roadways where connected vehicle communications were occurring and quantifying those environments using geospatial analysis and communicating the results of these analyses to researchers and technology developers in order to refine the technologies within environments where connected vehicles were having issues. And so I might be able to skip some things. Does everyone here know what a connected vehicle is? Or does anyone not say that? Okay, really briefly, so connected vehicles communicate information wirelessly between each other, vehicle to vehicle, or between the vehicles and the infrastructure, or vehicles to anything, pedestrians, cyclists, trains, and that communication is largely GPS-based because they're communicating their location and creating a path history so that the algorithms on board can calculate whether vehicles are on a collision course. And that specifically is a vehicle-to-vehicle application for safety alerts, and those safety alerts being something like forward collision warning or lane change warnings. And those imminent safety critical alerts are communicated through DSRC, dedicated short-range communications, which is low latency, communicating that robust, secure information, but it's only within a short range, under 300 meters. Anything else like infrastructure communications is often done through cellular or other information communications. So the problem during the course of this project was that we knew that connected vehicle performance was degraded in areas of high occlusion, and high occlusion being deep urban canyons where there's a lot of buildings flanking the roadway, or areas of high vegetation occlusion, very rural environments. And so for this specific research project, they had some needs to model what was going on around where these vehicles were communicating, specifically where the safety application alerts were occurring, and quantifying what was going on with regard to the sky occlusion specifically, because it does rely fairly heavily, or did rely fairly heavily on GPS. And finally, the outcome of this project was to create a web mapping product for visualization so that all of that information could be displayed to the researchers and these technology developers so they could do further testing in the environments of interest. Skip that. So starting off with data acquisition, these vehicles ran for about a year. So we had alert locations. There were 891 alerts, I think. And so we had points, latitude and longitude, and other related information regarding where those vehicles were communicating, where those alerts were going off. We also had location variables regarding the GPS, including dilution of precision, and visible satellites, information like that, and other things like performance variables, which came directly from the vehicle network data. That's where the vehicles themselves were instrumented, and things like speed or throttle position, as well as accelerometer, radar, other variables were available for teasing out where the issues were. So first, we need to get the model of the environment. And so we explored a few different methods. And for this project, in the interest of time and budgetary constraints, LIDAR looked very good, but was it available? And we found that, yes, it was available in our area of interest, which was 220 square kilometers, fairly large. So when you're talking about this size of an area, one of the ways that you can address this is using aerial LIDAR, which differs from mobile collected LIDAR because this is collected from an airborne sensor, and the first return being that first reflection off the top-down surface. So that's like the top of buildings, top of trees, and where there's no obstructions, that's the earth. So we used GIS software to look at this last data set and pull out those first returns and create a 1-foot resolution raster to represent the the surface of the Earth, the digital surface model over the entire area of interest. And so then spatial analysis, we used Esri ArcGIS to do this. There's the 3D Analyst and visibility tool set, and specifically the Skyline and Skyline graph to do this part of the research. So the connected vehicle alert locations where these safety alerts went off were overlaid on this digital surface model. And what this Skyline analysis does is you can set it up in different ways, but for this one we looked 360 degrees around the vehicle in 1 degree increments and looked upward to see where the last point of the obstruction point was that separated the physical Earth, the digital surface model, from the sky. So what that ends up being is, as you can see on the right in the image, is 360 points around the very light cyan at the top, representing the vehicle. And you can see the polar graph. And what comes out of this is percentage of open sky viewable from that exact location. Other information, maximum zenith angle mean that we use in our calculations. So preparation for the eventual products, there was a little bit of additional analysis and data prep. We used Spatial Analyst, 3D Analyst, to derive zonal statistics for building footprints. And what that means is a lot of times with aerial LIDAR, you'll get an extra bit of information, which is basically the polygons that outline a building structure. And that's really helpful for planning departments, local government. And so those are building footprints, but they're flat. And so what we did was take those polygons, overlay them on this digital surface model that we created, and extract zonal statistics, which is average height underneath that polygon, or maximum height. For our purposes, I think we used average height. And what that is just a simple representation of the building. And also created height-aware features so that those alert points weren't only at the lat long. They also had an elevation measure on top of the digital surface model. So where the antenna was located on the vehicle was actually represented in the eventual web map. So visualization using ArcSeeing. We have the CV alert locations. They are a point, which here is represented through that green flag. Skylines, the percentage open sky, that information is that line surrounding the connected vehicle there. Trees were represented, so trees were a local government-sourced information, so the city-owned trees that they were maintaining. Streets, so everything, all these things can be created and made into 3D features for 3D mapping needs. So we looked at 2 different types of interactive web maps. For the first being just a 2D, just a very simple representation of what was going on, so that researchers, technology developers, could interact with this map and get a little bit more information. So where we identified where the issues were happening, this gives them an ability to look at it and just explore a little bit deeper. So point and click, it gives you, this one is just aerial imagery, and the connected vehicle points being overlaid on that aerial imagery and any other information such as that skyline graph, the lines. So a very familiar technology, familiar way of mapping. So we used ArcGIS API for JavaScript, and it was used to call this hosted map. So basically you create the map and host it on ArcGIS online, and that can be a private or public thing. For our purposes, it was private. So, and then called back to a web page interface for access. And then we explored this 3D web mapping technique, and for our purposes, we used a City Engine. This was hosted locally on a server that could be accessed through, securely accessed. This a more advanced exploration tool, but it's still familiar. It's just like Google Earth, really. There were some issues with processing memory and that we ran into. So we were only able to achieve a partial map here, but this partial scene where you see the pyramids, those are the actual alerts occurring on the Earth, and those extruded buildings, that we prepared before, allowed you to get down even to the level of the vehicle and really explore the environment, what it looked like from the ground. So limitations of this approach, first it's the topographical model. If you think about it, so we use this publicly available LIDAR data set and it's aerial, but LIDAR like this is often acquired during a short period of time. It's finite, right? It's, say it took 1 month to collect, and say that month was September. Well, if you live around here, you get 4 seasons. So especially with vegetation in mind, at this time, I think that the LIDAR was collected with leaf on when the trees, everything was in full bloom. But if you collect LIDAR during the winter months, there will be leaf off, so it's going to look a lot different. And this data set, this data was collected over a period of a year, so we saw all seasons, so there's some error there. The other thing is, I think the data set was a year or 2 behind when the experiment actually took place, so the LIDAR data set. So the built environment could also have changed. New buildings could have been built, new streets could have been redone. So some errors there. And we were unable to obtain that complete result for the 3D mapping product, but that partial result did provide that general understanding and proven method to those that were interested that they could see this, use this visualization technique to really understand the environments and use that in further testing. So future work, really like to explore the issues related to obtaining that 3D mapping product. And as connected vehicle technology has advanced, use these refined methods because there is further refinement of the technology that needs to occur. So communicate the results using these methods to technology researchers and developers. Any questions? Sure.
The connected vehicles, are they just your vehicles or are they any vehicle that's around the road?
So connected vehicles have specialized instrumentation technology on them. They're not any vehicle. They're the vehicle that has that technology that's able to communicate with other vehicles. So for this experiment, they weren't personally ours, but we were doing a research project for a sponsor, and so that sponsor had these vehicles. So.
Can your technology detect any vehicle?
Connected vehicles, no. So an uninstrumented or vehicle without that technology, no, it's not going to be able to communicate with that. So that's when other sensors come into play, which automated vehicles have, right?
So vehicle to vehicle then requires GPS to get its location. It's not just car to car.
So not just GPS, especially at the time of this project, GPS was the primary location information, but there's.
It would share it with another vehicle, but it would get it from GPS. That's why it's line of sight, sky, and all that was the point.
Yes, absolutely. There's other sensors that come into play now, X, Y, and so it helps to where GPS is lost or location is not is known to not be perfect at that time. It can use dead reckoning to better estimate the location.
How far can LIDAR detect the object from sensors?
Ooh, that's pretty technical. I mean, it's a pulse of light, so distance of the ability for the light to go and return. I would say I can't give any measure there. That's not my field of expertise. Yeah, definitely. Does anyone know?
Let's read it tomorrow. We can save your questions for after, perhaps.
I was just going to say it's the basic thing.
Okay, great.